All right, in this next batch of video lectures, we want to talk about the shape of a graph. So what do we mean by shape? So where is it increasing? Where is it decreasing? Where is it concave up and where is it concave down? So we'll look at those couple features and we'll use some derivative tests in order to determine, when and where those things are happening. So let's just make a definition really quick. So let f be some function defined on an open interval from a to b. We will say that a function is increasing if whenever x1 is less than x2, that means that f of x1 is less than f of x2. And I'm going to go ahead and draw a picture of that in the next frame. And then we'll say the thing is decreasing when x1 less than x2 implies that f of x1 is bigger than f of x2. Constant means if x1 less than x2 means f of x1 is equal to f of x2. And these things need to be true no matter which x1 and x2 that we choose in this open interval. Okay, let's look at some pictures of these things really quick. All right, here's a couple of pictures at least for increasing and decreasing. So here's an example of a function that's increasing on the interval from a to b. So when you read this thing from left to right, the function is increasing, right? And notice that when x1 is less than x2, then f of x1 is smaller than f of x2. Right, and the opposite situation happens for a decreasing function. So here we've got x1 is less than x2, but f of x1 is greater than f of x2. And so what do we mean when we say constant? Well, f of x1 would be equal to f of x2, so we would just draw a horizontal line. So a constant function is just a horizontal line. So these things have to be true for any x1 and x2 that I pick in the open interval from a to b. So the question is, how do we determine when a function is increasing and when a function is decreasing? Well, if you look here at any point in the interval, what can you say about the slope of the tangent line? Well, that's going to have positive slope, right? So any tangent line that I draw is going to have a positive slope. So that's probably something to note. So f prime of c is bigger than 0, right? So the derivative is positive. The slope is positive at any point c that I choose in the open interval from a to b. And then what about when the function is decreasing, right? So no matter where I draw a tangent line in the interval from a to b, the slopes are going to be negative, right? So f prime of c is going to be negative, right? The slope is going to be negative for any c that I pick in the open interval from a to b. So that's actually a theorem that we'll write down, and we'll actually do a quick proof of the theorem using the mean value theorem. Okay, so here's the theorem that we alluded to just a second ago. So let's let f be a differentiable function on the open interval from a to b. If f prime of c is positive, so if the thing's got a positive derivative everywhere in the open interval, then f must be increasing, right? If the derivative is negative everywhere in the open interval, then the function must be decreasing. And if the derivative is 0 everywhere in the open interval, then the function must be constant. We actually proved this in the section on the mean value theorem, so we won't need to prove it again. But just so you can see how it fits in with this first derivative test, let's go ahead and prove item 1, and we will use the mean value theorem to do that. Okay, so we've got that f is a differentiable function on the open interval from a to b, and we know that the derivative is positive everywhere in the open interval from a to b. So we want to show that f is increasing. So what does it mean for a function to be increasing? Well, I need to choose an x1 less than x2 and show that f of x1 is smaller than f of x2. So that's what we need to show. So let me choose any x1 and x2 in the open interval from a to b such that x1 is less than x2. So remember, f is differentiable everywhere on this open interval. That means it's continuous, and so that means that we can apply the mean value theorem to f on this interval from x1 to x2. So that's basically the trick, right? So we can find a number c in the open interval from x1 to x2 such that f prime of c is equal to the average rate of change of f on this closed interval. Right, so f prime of c is equal to f of x2 minus f of x1 over x2 minus x1. So we know that this thing, that f prime of c, we know that that's a positive number. That means this fraction must be a positive number, right? So this fraction is greater than 0. And we know that the denominator, right, that's also a positive number because x2 is bigger than x1. So x2 minus x1 must also be a positive number. So I can multiply both sides by x2 minus x1, and that's not going to change the direction of the inequality. So I know that if the fraction is positive and the denominator is positive, that means that the numerator must be positive, right? So f of x2 minus f of x1 is greater than 0. So now just add f of x1 to both sides, and that says that f of x1 is less than f of x2. And that's what we needed to show, right? We suppose that x1 is less than x2. We need to show that f of x1 is less than f of x2. That's what we got. Therefore, the function is increasing. It would be a great idea if you were to go and prove that if the derivative is negative, right, follow this same line of proof to show that the function must be decreasing.